What I'd like to demonstrate here are some simulations related to what you will perform in your lab this week. So the first experiment that I have here is what's called an electroscope. Now, of course, the pluses and the negative signs have been added here for visual representation, but all an electroscope is basically a charge detector. It determines whether or not you have charge on an object, because in reality, you're not going to see little blue circles with a little dash through it. You won't know if there's charge on it. So how might you test if there's actually charge present on an object? Well, that's by what's this device known as an electroscope. And an electroscope is simply a flat metal plate with a metal bar down the center with two metal tines at the bottom, and those metal tines are free to move back and forth. So they're basically freely on a pivot, and then there's this insulating ring that goes around. And given that this is a metal, the electrons are free to move. Now I'm going to bring a negatively charged rod towards the plate, and what you can see happens is as this charged rod gets closer and closer, it basically pushes the negative charges away from the negatively charged plastic rod, which is an insulator, and they move down the tines, and then these tines begin to repel each other. Now, that would indicate that there's actually charge located on this rod. But for example, if there was no charge on this plastic rod, those tines wouldn't respond at all because there'd be nothing to push away the charge. All right, now, if I bring this finger here and touch the oscilloscope, well, the oscilloscope has now, in a sense, become charged because the electrons, a bunch of electrons actually drained off onto the finger, and now when I pull the rod away, the tines are again repelled from each other because you can see there's some electrons that are actually missing here. So this whole system, the charge which has now spread out uniformly over this electroscope, is positively charged, so the tines repel each other even when the finger is apart, or even when both of the finger and the rod are far apart. If I bring the finger close, and those electrons get deposited back onto the electroscope, now it's electrically neutral and the tines just hang vertically. So an electroscope is simply a device that measures whether or not you have charge that is present. Next, I'll demonstrate what's called the Triboelectric Effect. So here's a fuzzy cat with a nice big comb, and the comb, while being plastic, is an insulator, and the fur is also an insulator, and we might not know ahead of time, which one of these materials, the hard plastic or the fuzzy fur, has a higher electron affinity when I rub them together with friction. That's what the triboelectric effect is. It basically is a charging by friction. Now, if I begin to charge here, what we see is the cat becomes positively charged because the plastic has a higher electron affinity. Now, interestingly enough, it doesn't take too long before those electrons that built up on the comb actually get bumped back onto the cat again, and just get pulled back and basically neutralize things again. If the comb, like I said, there's lots of other factors that can basically pull that charge back to where it was here, right? But the cat can be charged just by combing like this, stripping the electrons off the cat, depositing them on the hard plastic comb. So the triboelectric effect describes this charge by friction, and it does depend, of course, on depends, of course, on the types of materials that are being rubbed together. All right, next, let's look at charge by induction. Now, what is charge by induction? Well, here what I have is I have two conducting metal rods. These are neutral metal rods, and they're sitting on glass, and glass is a good electrical insulator. So I'm going to take those two rods and I'm going to actually push them towards each other so that they're in contact. And notice that as soon as I do that, as soon as I put them in contact with each other, the electrons are being shared between the two conductors. It's behaving like one giant conductor. Now I'm going to take this charged plastic rod and I'm going to bring it close to, but not touching those two plastic, not touching the long metal rod. And then I'm going to take the metal rod that's over here. Well, before I do anything, notice what happens. Well, this is a conductor, so electrons are free to move, and a lot of them kind of get pushed over towards this end. Not all of them, because it's harder and harder to push them over there once you put one there, and then two there, and then three there. It becomes, there's a repulsive force that's built up there that keeps it from moving over there. But basically what you see is the very right end of the rod, this end right here, starts to build up a negative charge, and then the left end builds up a positive charge. So there's been charge being polarized on this conductor. Now, if I break the conductor at this point, those electrons now, those extra electrons, they more or less just freely distribute themselves over the surface of the conductor. Now, this conductor now has a net negative charge. And if I move that charged body away, those electron deficient piece of the conductor, and they also distribute themselves evenly. So now we actually have a positively charged a metal rod and a negatively charged metal rod, and we've charged these two by induction. We first polarized it, which means we induced a charge on one side and induced a charge on another side. Then we broke it in half, and the conductor ended up with a charge. So looking at a conductor, what happens on a conducting square, for example? Well, look at all these electrons. You can see they're slowly some of them are kind of jiggling about a little bit, and they're trying to reach what's called electrostatic equilibrium, meaning they're all trying to minimize their surface energy by getting as far apart from each other as possible. But that means they want to kind of smoothly spread themselves out over the surface of the material. So here I have a square, but I could also look at a bar, for example, where the electrons very, very quickly, in a time frame we call the relaxation time, they want to arrange themselves in order to find an orientation we call electrostatic equilibrium. Now, what about a circle? The electrons jiggle about really, really quickly, and then they find their equilibrium configuration. Now, something I should notice here, this is a thin conductive circular plate, is this time, in reality, this relaxation time is on the order of nanoseconds. So it happens very, very quickly. Notice also, too, that the edges of the plate seem to have a higher charge density than when you're on the surface of the plate, kind of not at the edge. And that's because the curvature is the greatest at the edges, so there's not as many nearest neighbors. Now, what about a triangle? Here you can see what I mean. We've reached our state of electrostatic equilibrium, and the charge density is definitely highest right at the corner of the triangle. That's where the most charges per unit area are located. That's what I mean by charge density, charge per unit area. And that's because there's not as many nearest neighbors to basically push away when you're at the corner. Here, there's only really 1, 2 that are really pushing, so they can really get closer, whereas this charge, for example, has to contend with all of these charges everywhere from each side. Now, notice that this situation is not truly static because everything is kind of moving a little bit. There's a lot of, on a microscopic level, there's a lot of things that are happening that actually cause the charge to move. So it's not completely static. So finally, example, here I'm going to look at a wool sweater and a balloon, and then a wall. Now, right now, nothing really happens. And in reality, we're not going to see plus charges painted red and negative charges painted blue, but really it looks something like this. But I'm going to add the charges on here because it paints a nice picture for us to understand what's actually going on. Now, rubber is a good insulator and wool is a good insulator, but which one has a higher electron affinity? Well, that's a detailed question from surface chemistry, which would be kind of hard to answer. But let's just rub them together, and we see the rubber actually picks up all those electrons just by the actual physical, rubbing between those surfaces. Now the balloon has a bunch of negative charges. So if I release the balloon, it's attracted to the sweater because it has all those charges that are built up on the surface that was rubbed against. Now this balloon, if I take it to the wall, let's say the wall is made of wood, wood's a good insulator, those electrons don't really want to move, but they will be kind of pushed or stretched. Or what can happen is the insulator can become polarized, and there still is an attractive force here. Not because the wall has become charged, but just because the negative charge on the balloon has stretched or distorted what's called the electric dipole of the individual molecules inside the wood, and created actually an electrostatic force which can be measured. This force is pretty small, but if you have enough charge built up, you can actually measure it electrostatically. So these are some of the experiments that you'll be looking at in this week's lab and some of the theory that goes behind with it.